Good evening, everyone. Myself, NAMRATA MUNDARGI, a research scholar pursuing PhD under the guidance of Dr. K. Sujata, Department of Chemistry, Karnataka University, Dharwad. My topic is green root synthesis, characterization techniques of silver and vanadium nanoparticles using CDM GUJAVA leaf extract. My paper ID is 230. An introduction. Nanotechnology is a relatively emerging field of science that involves the synthesis of different nanomaterials. The nanomaterials can be synthesized by various techniques such as chemical, physical, and the biological methods. Green synthesis is a safe, non-toxic, ecologically benign, and clean way to create the nanoparticles. The synthesis of silver and the vanadium nanoparticles by Pysidium guajava leaves extract, which contains various compounds like gallic acids, and the flavonoids such as catechins, camphorol, and the quercetin, in which the quercetin that act as a reducing and the stabilizing agent. The synthesized silver and the vanadium nanoparticles were characterized by UV visible spectroscopy, FTIR, X-ray diffraction, and the scanning electron microscopy. Materials and the methods. The fresh leaves of guava leaves were collected from the botanical garden of Karnataka University, Dharwad. They are washed under the running water, which is followed by the double distilled water. The dried leaves were powdered, and they are extracted with the ethanol solution. After extracting, reflexing for 3 hours, the hot solution is filtered. The filtrate is concentrated and to get concentrated to get the crude compound. The crude compound is tried to soluble in the ethyl state. So part of the crude compound is soluble in ethyl state, and part of it is insoluble in ethyl state. The ethyl insoluble part contains usually the quercetin compound. Okay. These are the phytochemical screening for the leaves extract. We have considered the 5 different tests for the conformations. That is the test for the alkaloids. 6 drops of Wagner reagent were added to the 2 ml of crude extract. The formation of brown or the reddish precipitate confirms the alkaloids are present. For the test of flavonoids, crude extract were treated with a few drops of hydrochloride solution. Intense green color confirms the flavonoids are present. Test for the phenols, a few drops of ferric chloride solutions were added into the crude extract. Appearance of bluish black color. And further, the test for the terpenoids and the test for saponins confirms the observation by formation of reddish brown and the formation of the foam colors presents the terpenoids and the saponins are present. This is the characterization of the synthesized nanoparticles from leaf extract, in which we have extracted the quercetin. We can see that is the main peak at 3,331.87 per centimeter represents the phenolic OH, and 2918 represents the CH stretching, and 1687 represents the carbonyl stretching frequency, and similarly 1609 represents the CH stretching frequency. Whereas in case of UV visible spectrum, we can observe the 2 bands at 274 and 355 for the flavonol groups. This is the structure of the quercetin. We have synthesized 2 different nanoparticles, that is silver oxide nanoparticles and vanadium oxide nanoparticles. In case of silver oxide nanoparticles, we have used the silver nitrate in the ratio of 2:3, and the temperature we have given the 60 degrees Celsius. We took the time of 3 hours for continuous stirring and heating, and color change confirms the present formation of the silver oxide nanoparticles. Usually, almost all the leaf extract will be acidic in nature, and after we have, during formation of the nanoparticles, we have used the sodium hydroxide as the basifying agent. Hence, we have got the pH as 10 in case of silver oxide nanoparticles, whereas in pH 12 in case of vanadium oxide nanoparticles. These are the FESM images of the silver oxide and the vanadium oxide nanoparticles. Usually, the SEM morphologies vary from different nanoparticles. Some are angular, spherical, and etc. This is the FTIR spectrum of the silver oxide nanoparticles, in which 3,358.5 58.02 centimeter confirms the phenolic OH, and 2924 and 1627 and 1376 per centimeters represents the silver oxide nanoparticles, and 1689 represents the carbonyl stretching frequency. In case of UV visible spectrum, silver oxide nanoparticles, we have got the two band A and band B at 278 and 410 nanometer. In case of powder XRD, crystalline structure observed for the Bragg's angle 2 theta at different angles like 20. Okay, Bragg's angle we have observed at a different 2 theta angles with respect to the intensities, whereas in case of EDX we can confirm the formation of silver, carbon and the oxygen atoms are present. In case of FTIR vanadium nanoparticles, we have observed the phenolic OH at 3390 per centimeter, whereas 2819 and 1376 and 719 represents the vanadium and oxygen bonding. And this is the FE-SEM image of the vanadium oxide nanoparticles. This is the powder XRD of the vanadium oxide nanoparticles. We have got different values for this. And for powder EDX, we have confirmed that carbon and oxygen are present for the vanadium oxide nanoparticles. The present study demonstrated the extraction of quercetin from PSIDIUM GUAJAVA leaves, which was confirmed by the FTIR and UV visual spectroscopy. The crude product was further carried out for the synthesis of the nanoparticles, which acts as a capping and the stabilizing agent. We have synthesized the silver oxide and the vanadium oxide nanoparticles from PSIDIUM GUAJAVA leaf extract, which was confirmed by the FTIR UV spectroscopy, powder XRD, EDX, and FE-SEM. Thank you.
Please start.
Good evening, everyone. My name is Shivanshi Tyagi. I'm a research assistant at Amity Institute of Biotechnology, Amity University, Uttar Pradesh. Today, I'll be presenting on the topic microbial immobilization techniques for enhanced dye degradation and textile wastewater remediation. First, coming to what is the need for dye wastewater treatment and what are the complications associated with it. First is the untreated effluent release. The effluents discharged by the textile industry in their untreated state consist of a wide range of organic contaminants, including the unfixed dyes, acids, alkalis, detergents, bleaching agents, and heavy metals. Second is the agriculture impact in Asia. For decades, farmers in India, Bangladesh, Vietnam, and Indonesia have been using untreated effluents for irrigation, damaging the soil quality and crop health in the longer run. Third is the economic impact. Toxic effluents for irrigation leads to decreased agriculture productivity and impact the GDP of the country. Then comes the environmental consequences. So the reduced light penetration into the water affects photosynthesis and the health of the aquatic plants, lowering the BOD, COD, pH, and dissolved oxygen of the water bodies. And when ingested by aquatic organisms, it leads to harmful metabolic intermediates accumulation inside their body and which further travels into the food chain. Coming to the human health risks associated with these dyes is that dye from this industrial effluent pose health risk as humans ingest it or come in the contact of these dyes through skin contact. The intestinal microflora convert these azodyes into toxic amino acids, harming human tissues, further leading to organ damage, tumor formation in various organs, and cancer. So, coming to why there is a challenge in textile wastewater remediation. First is the complex chemical structures of these dyes. The intricate composition of textile dyes makes their degradation challenging and resource intensive. Coming to environmental regulations, there have been laws for the disposal of this water, but many small-scale industries do not follow, as this is a cost. It is an expensive process, and the conventional methods which are widely available are actually inefficient and expensive, and that is the main reason the small-scale industries are not following these laws. So bioremediation here plays a very important role. Today, I'll be talking about microbial bioremediation. The microbial bioremediation.
Excuse me, Shivanshi.
Yes, sir.
You're requested to keep your camera on as per the instructions from the organizers.
Yes, sir. Yes, sir. Just a minute. So am I visible right now? Hello?
Hi.
Am I visible? Hello?
Yeah, please go ahead now.
Yes, sir. So coming to microbial bioremediation, the microbial bioremediation offers a sustainable and effective method for removing these dyes from industrial effluents by harnessing the natural capabilities of these microorganisms like bacteria, virus, algae. This technology mitigates the environmental impact of dye pollutants and presents a viable alternative to conventional treatment methods. There are several methods or mechanisms by which microbial dye degradation occurs. First is the biosorption. It involves the adsorption of dye molecules onto the microbial cell walls. This process effectively removes dyes from solutions, allowing them to be separated from the cells and safely discarded or treated further. Second is bioaccumulation. In this process, microorganisms take up or store dyes within their cells. This mechanism can be particularly useful for concentrating or isolating these dyes from the contaminated environments. Third and the most important is enzymatic pathways. Enzymes such as lacase, peroxidase, or azoreductase catalyze the breakdown of dye molecules, facilitating their removal. Lacase, for example, oxidize the dye molecule, while peroxidase and azoreductases specifically target and reduce the azo bonds in the azo dyes, effectively breaking down the complex structures of these pollutants. So, though free microbe cells are effective, but immobilizing them onto a solid support or inside a solid support is more effective, which has been proven with studies. So coming to microbial cell and enzyme immobilization technique. Immobilization techniques involves fixing microbial cells or enzymes onto a solid support or within the matrices, allowing them for their retention and reuse in treatment system. There are three or four major techniques by which we can immobilize the enzymes. First is the entrapment into the polymers. Microbial cells or enzymes are covalently bonded. The entrapment method, where cells are trapped within the porous matrices like alginate or polyacrylamide, providing protection from external factors and high density cell density. Second is the adsorption onto the supports, where microbes or enzymes are physically adhered to the surface or a solid support like activated carbon, silica gel, alginate beads. This method is simple and inexpensive. Coming to encapsulation, microbes or enzymes are enclosed in semi-permeable membranes or capsules like silica gel, liposomes, etc., which helps protect them from harsh condition and maintain them for higher reuse capabilities. Covalent binding to the carriers, microbial cells or enzymes are covalently bonded to a functionalized carrier using chemical linkers for strong and stable attachments. Example, magnetic nanoparticles or chitosan beads. These are some of the carriers. Microbial cell carriers must be insoluble, non-biodegradable by the biomass, non-toxic, inexpensive, and easy to handle and reuse also. So the carriers are The selection of the carrier or support material is very important decision to be made in an immobilization process, as it affects the viability of the immobilized microbes and therefore affects the efficiency of dye wastewater treatment processes. These are the carriers widely used for dye degradation studies.
First, you have 1 more minute, so please.
Yes, sir. The benefits of immobilization of cell or microbes is that the stability is improved and microbial activity is enhanced. Third is the ease of separation and reuse, as I'll be showing in another study, and higher loading capacity. These are some of the studies that has been done on immobilized microbes. First was from G et al. In 2004, who studied the decolorization of basic blue dye using Phanerocytus ordida immobilized on discs in a rotating biological contactor. They achieved 78% efficiency. So as I was explaining that reuse is possible. So just focusing on the last study by Beckett et al. In 2020, who concluded that Enterobacter cloacae, A3 coated with magnetic iron oxide nanoparticles decolorized 91.60% of basic red 46 azo dye, 2200 ppm in 24 hours, and it was reusable up to 4 cycles. And after 4 cycles also, it showed effective results. The future prospects of microbial immobilization are the emerging technologies. Nanomaterials like nanotubes, nanoparticles can be used. Bio-based carriers, which are environment friendly, can be used. Smart materials like stimuli responsive polymers can be utilized, which change their properties according to the external factors. And the integration of 2 or more processes like advanced oxidation process, membrane bioreactors can be useful. And scalability, these studies can be upscaled in pilots, and pilot scale studies can be upscaled. Conclusion: immobilized cell systems offer several advantages over suspended cells, including enhanced stability, continuous operation, simpler solid-liquid separation, and increased resistance to harsh conditions. Research have shown that immobilized cells are effective in biodegrading various wastewater contaminants. Adding nanomaterials like iron oxide nanoparticles can further improve their efficiency. And further future research should focus on developing new and cost-effective carriers, increasing biomass concentration, and extending the lifespan of these carriers. Thank you.
So today I will talk about chalcogenide-based thermoelectric materials. This is a review. So what is first we will talk about thermoelectricity. Thermoelectricity basically means thermo plus electricity. It means conversion of heat into electricity. So thermoelectricity refers to the direct conversion of temperature difference into electrical voltage and vice versa. This thermoelectricity, it works on 3 principles, that is Seebeck effect, Peltier effect, and Thomson effect. Seebeck effect, it was discovered by Thomas John in Seebeck in 1821. It occurs when the temperature difference between 2 different semiconductor materials generates a voltage. This generated voltage is directly proportional to the temperature difference, as we can see by this formula. Next, the Peltier effect. It was discovered by Charles Peltier in 1834. It states that when an electrical current flows through a circuit into different conductive materials, causing heat to be absorbed at one junction and released at the another junction, it is utilized in thermal cooling. Next is the Thomson effect. It was discovered in 1851 by Thomson. It describes the heating or cooling of a single conductor carrying an electrical current when there is a temperature gradient along its length. Next, we will talk about the criteria for the selection of thermoelectric materials. The potential of the thermoelectric material is determined by a dimensionless figure of merit ZT, which is equal to alpha square sigma T divided by K, where alpha is the Seebeck coefficient, sigma is the electrical conductivity, T is the absolute temperature, and K is the thermal conductivity. This K kappa. The thermal conductivity is contributed by lattice thermal conductivity and the electrical thermal conductivity. For a material to have to be good thermoelectric material, it should have high value of ZT. It means it should have high value of Seebeck coefficient, high value of electrical conductivity, and low value of thermal conductivity. Also, there is a term power factor, which is the ability of the material to produce useful electrical power. The power factor is defined by alpha square sigma. It means power factor depends upon Seebeck coefficient and the electrical conductivity. Then we will talk about chalcogenides. What are chalcogenides? Chalcogenides, these are the compounds containing chalcogen elements. It means group 16 elements, that is sulfur, selenium, and tellurium. Chalcogenides, they have high Seebeck coefficient, which means Seebeck coefficient measures the voltage generated in response to a temperature difference across the material. High Seebeck coefficient indicates that material can convert heat to electricity efficiently. So chalcogenides having high Seebeck coefficient, we can say these are the good thermoelectric materials. Also, chalcogenides have low thermal conductivity, which minimizes the loss of heat through the material. Low thermal conductivity is crucial because it helps in maintaining a temperature gradient, which is necessary for generating electrical power. Chalcogenides have high electrical conductivity, allowing for efficient charge carrier transport. Also, in this equation, the three main parameters, the Seebeck coefficient, electrical conductivity, and thermal conductivity, they are all interrelated. So enhancing ZT of the material is challenging task. We have to increase electrical conductivity without significantly increasing the thermal conductivity, which is a challenging task. Balancing high electrical conductivity and low sigma is key to achieving a high ZT. Also, when we talk about the band structure of chalcogenides, they have narrow band gap, which can optimize the carrier concentration and improve the power factor. Chalcogenides have good chemical stability, which is essential for the reliability of thermoelectric devices. Stability under thermal cycling is particularly important for practical applications. The strong electron-phonon coupling in the chalcogenides can enhance the Seebeck coefficient without significantly increasing the thermal conductivity. This strong electron-phonon coupling is beneficial for maintaining high thermoelectric efficiency. Next, here are some of the chalcogenide-based thermoelectric materials. First is bismuth telluride, Bi2T3. It is most commonly used thermoelectric material near room temperature. It has high ZT and is used in devices like Peltier coolers and thermoelectric generators. Lead chalcogenides. In lead chalcogenides, we have PBTE and PBSE. Lead telluride, PBTE. It is the most promising thermoelectric materials in the mid-temperature range. It has high Seebeck coefficient and low thermal conductivity. PBSE lead selenide is referred to as sister material of PBTE. It is used for thermoelectric materials in the mid-temperature range. This PBSE lead selenide offers a good balance of electrical and thermal conductivity. Next, we have tin chalcogenides. Tin selenide, it has gained significant attention due to its record high thermoelectric performance, especially in its single crystal form. Tin selenide exhibit low thermal conductivity and high Seebeck coefficient. Tin telluride, it offers good thermoelectric performance when doped with other elements. Next is antimony telluride. It is often used in combination with bismuth telluride to create alloys with enhanced thermoelectric performance. Copper chalcogenides, these are used at high temperatures. It exhibits a good combination of high electrical conductivity and low thermal conductivity. This is the literature survey for lead telluride doped with thallium. A high ZT value of 1.5 is observed at 773 Kelvin. For bismuth telluride doped with antimony, a ZT value of greater than 1 is observed at 600 Kelvin. Similarly, for other lead chalcogenides, PBSC, lead selenium, ZT value greater than 1 is also observed. These are all experimental results. In computationally, for PBSC, a ZT value as high as 2 is also proposed by David Parker. Next is, how can we optimize the electrical and thermal properties of chalcogenides to enhance the thermoelectric property of chalcogenides? We can use the techniques. First is doping. Doping with suitable elements can adjust the carrier concentration to an optimal level which increase electrical conductivity without significantly increasing the thermal conductivity. Doping can also modify electronic band structure to enhance electrical conductivity. Next is nanostructuring. Creating nanostructures with numerous grain boundaries can scatter phonons more efficiently than electrons, which reduces the thermal conductivity while maintaining good electrical conductivity. Allowing forming solid solution with other materials can reduce thermal conductivity through increased phonon scattering, which maintain electrical properties. Isoelectronic substitution, it means
Excuse me,
substitution of
Isha.
atoms with similar electronic properties can tune the band structure and the carrier concentration. Next is the defect engineering.
Isha, please try to wind up in
Defects
your
can scatter
presentation in
phonons,
next 1 minute.
reducing kappa without adversely affecting the electrical conductivity. Dimensional reduction, reducing the dimensionality of the material to thin films and nanowires can enhance the Seebeck coefficient and reduce the thermal conductivity due to enhanced boundary scattering. The strain-induced band modification by applying mechanical strain can modify the electronic band structure, which can increase the Seebeck coefficient and the electrical conductivity. Here are some of the uses of chalcogenide-based thermoelectric materials. These are used in power generation. As we know that most of the heat is wasted in the thermoelectric materials. They utilize this waste heat and convert this waste heat into the useful energy. They are also used in remote and off-grid locations where conventional power sources are not available, such as space missions and remote sensing devices. Chalcogenide-based thermoelectric materials are also used in cooling applications. These used Peltier effect. The cooling application thermoelectric materials, they use Peltier effect to provide precise temperature control in applications such as electronic component cooling and refrigerations. These are also used in space applications, particularly lead telluride. It is used in space applications. Radioisotope thermoelectric generators provide long-term power for space missions such as those by NASA. Chalcogenide-based thermoelectric materials are also used in industrial applications for heat recovery. The heat which is wasted through large instruments such as furnace and other high-temperature equipments. Chalcogenide thermoelectric materials are also used in industrial applications and in temperature regulations. Thank you.
Your time is up. Thank you.
So, good evening to respected session chair. My name is Sahil. I am pursuing PhD in physics from UPS Dehradun under the guidance of Dr. Manjit Singh Goyal and Professor Ranjit Kumar Bejpuria. So today's presentation title is MXene synthesis properties and application in advanced energy storage technologies. So these are the outlines of today's presentation. So need of electrochemical energy storage devices. So electrochemical energy storage is essential for stabilizing renewable energy sources and providing reliable power supply, ensuring efficiency and sustainability in energy systems. It supports the transition to clean energy. So here is the pros and cons associated with renewable energy. So the pros is it is eco-friendly, reducing reliance on fossil fuels, and the cons is high initial cost, and solar and wind energy are weather dependent and may not provide consistent power. Geographical limits. So to overcome these limits, we need electrochemical energy devices to store the energy. So these are some existing energy storage devices such as capacitors, supercapacitors, and batteries. So as shown in figure, it shows a Ragon plot. So Ragon plot is the plot that energy density of system as shown on y-axis, and against its power density on x-axis. Ragon plot is used to compare the performance of different energy storage devices such as battery, supercapacitor, fuel cells as shown in figure. So there are various electrochemical devices such as smartphone, laptop, electrical vehicle, and wristwatch, LEDs, headphones that we utilize in day-to-day life. So importance of nanostructure material in electrochemical energy storage devices. So different dimensional material like 0D, 1D, 2D, 3D materials play a crucial role in enhancing the performance of electrochemical energy storage devices because of their high surface area, high ionic diffusion pathway, and structural stability, then enhance its specific capacity and capacitance. Nowadays, two-dimensional materials show a great interest in energy storage application. So why MXene? MXene showing a great potential for energy storage. It consists of a layered structure. So after synthesis of MXene, we get surface termination groups, and it consists high surface area, high electrical conductivity, high specific capacitance. So due to these features, we can enhance its energy density. Figure 1 shows the atomic structure of MXene, titanium carbide. So constituent of MX and MXene. The general formula of MX is shown in the periodic table, is MAXN, and the periodic table shows the elements. Here M is the early transition metal, A is silicon, aluminum, X is the carbon or nitrogen or both. So after etching process, we remove the A layer and we get TX. Here TX is oxygen, fluorine, and OH group, that is surface termination group. So there are various approach for the synthesis of MXene, like hydrofluoric acid, in situ etching, fluoride-free etching, and bottom-up etching method. However, in the future research, researchers are focused for the large production, green synthesis, low cost for the synthesis of MXene. So this slide shows the general method of the synthesis of MXene. Here, max phase, as shown in titanium, aluminum carbide, we stir with hydrofluoric acid, and after the stirring of 24 hours, we centrifuge it to maintain its pH, and we dry it. So the powder we get, as shown here, the MXene. It is multi-layer MXene. So it is multi-layer MXene as we talk about the morphological. So to make it single layer, we intercalate it using some agent like DMSO or TBOH, dimethyl sulfoxide, and we stir it till 16 to 24 hours. Then we dry it, and we get the delaminated single layer MXene. So in conclusion, hydrofluoric acid etching shows high yield than in situ acid etching, as shown in the figure. So recent development in MXene based material for energy storage. So nowadays, researchers are working on MXene based composite, because pristine MXene having some constraints like restacking and agglomeration. To overcome these issues, researchers are focused on MXene based composite like carbon based, with RGO, graphene, activated carbon, and with metal oxide, and with some connecting polymers. So there, table 1 shows advantages and disadvantages associated with the MXene based composite. So as we know, MXene carbon based composite having high electrical conductivity, high surface area, good cyclic stability, but limited pseudo capacitance, because carbon based material are EDLC type. And second one is MXene metal oxide based composite, which is having high pseudo capacitance, high energy density, but disadvantage is lower electrical conductivity compared to carbon material. And third one is MXene conducting polymer, which having good flexibility that can be used in flexible electronics and flexible supercapacitors and enhanced capacitance. But the issue is the stability issue, and moderate electrical conductivity. So this shows the research impact assessment. So the research impact assessment in MXene energy storage application visualized using VOS Viewer, a free tool for constructing bibliometric networks. So here are ranking of authors based on contributing articles shown in figure and table 2. So Yuri Gogotsi. So here Yuri Gogotsi is having highest research article and citation in MXene energy storage field. And table 3 shows the top countries having highest publication in MXene energy storage. And table number 4 shows highest occurred keyword, that is MXene, performance, nanosheet, etc. And in table 5, organization based on MXene storage documents. So challenges and future scope. So there are few challenges in MXene. First is the large scale production. Large scale production of MXene is difficult. Environmental stability and cost effectiveness, non-safe synthesis. As we use hydrofluoric acid and HCl acid, so it is not having safe synthesis, or we not having safe synthesis in MXene. Agglomeration and storage. MXene having a problem in oxidation, in environmental, if we take this material outside, so it oxidizes. So this is the problem. So the future perspective of this is the green synthesis of MXene, synthesis of new MXene hybrid, DFT modeling to predict the theoretical value of the capacitance, improve design of MXene-based energy storage devices. References. Thank you.
Respected session chair, distinguished colleagues, and fellow attendees. My name is Bhushan Kumar, and I am pursuing PhD from UPS Dehradun. My today's presentation title is State of the Art Developments in MXenes, a comprehensive review. These are the outlines of today's presentation, and this is the introduction of 2D materials. As we know, 2D materials are those materials which has one side are of nano size. Now, graphene is the first and most famous 2D material known for its high electrical conductivity and good strength. Nowadays, MXenes has been developed a novel 2D material which has many diverse applications due to its renowned properties. These are the various properties of MXenes, like hydrophilicity, high electrical conductivity, mechanical strength. It has good flexible, but most importantly, it has tunable surface chemistry and high surface area. So these are the constituents of MX and MXene. The periodic table is showing. This is the general formula of MX, Mn plus 1 AXN, where M is early transition metals shown in red color in periodic table. A is elements that is shown in periodic table, which is blue color, and X is either carbon or nitrogen or maybe both. This is the general formula of MXene, Mn plus 1 XN TX. Here TX is a surface termination group. It can be hydrogen, oxygen, fluorine, or chlorine. So this is the different MX phase structures, 211, 312, 413. And how we can transform MX into MXenes. So this is the totally transformation process. Now this is the MX phase. It has, we can see the different layers of M, A, and X. Now, if we remove a layer, so we can see after the removal of a layer, we will get MXene, and after the sonication, we will get a single layer MXene sheets. Now, this is the surface different surface termination groups. If we see the same micrographs, we can see the accordion-like nanostructure of this MXene. Now, this is the different synthesis approaches. So currently, we have two approaches to synthesize MXene. One is fluorine-containing route, other one is fluoride-free route. In fluorine-containing route, we have HF etching, and second one is in situ HF. So here in situ HF, we can use HCl, and as a fluoride salt, we can use potassium fluoride, lithium fluoride, and other and bifluoride-based reagent also. In fluoride-free routes, researchers are making fluoride-free routes also, and they are working. And these CVD, electrochemical etching, alkaline etching, Lewis, and many more, halogen etching also. These are the different properties of MXene. MXene has been synthesized in 2011. So these are the various properties associated with MXene. We can see the thermal conductivity. It has 722 watt per meter per Kelvin. Electrical conductivity, it has the electrical conductivity up to 25,000 Siemens per centimeter, which shows MXene Ti3C2TX, which has a thickness of 1.8 nanometer. Mechanical property, like it shows a tensile strength of 570 megapascal and Young's modulus 333 gigapascal in the case of Ti3C2TX MXene. And it shows a good AMI shielding capabilities also. It's the MXene, pure MXene, pristine MXene shows 116 decibel shielding effectiveness as compared to graphene. Graphene shows, the pure form of graphene shows 68 decibel. So its shielding effectiveness is much more. The specific capacitance also 654 farad per gram, and band gap and work function. So these are the various properties of MXenes. Now, these are the different applications of MXene. Nowadays, MXene is used in energy storage devices like batteries, supercapacitors, electromagnetic interference for the purpose of shielding, the sensors, optics, biomedicine, environment, and many more. So these are the different applications. Now, bibliometric analysis, it is a quantitative method to analyze scientific literature. So here we use Web of Science for our database, and WOS Viewer, this is the software we have used for generate this type of analysis. So here we can see in this diagram, we can see the maximum contribution in this area is coming from the China's. So we can see the number of publication which the China has produced 8387 and USA produced 1224. But if we see the citation to document ratio, the China's has 34. This ratio is 34, but USA has 103. So it means the USA is providing more. Means more important in this area as compared to most quality of papers the USA is produced. Now, this is the assessment based on participating in institutions. We can see the maximum number of publication is coming from the Chinese academic science, and the second position we have Drexel University, USA. We are the first MXene synthesized by Yuri Gogosyan and its team. And the citation to document ratio, the Drexel University has very large, that is 192. It shows the quality of literature produced by this Drexel University. Now, this is the assessment based on the authors. So in this category, Yuri Gogosyan topped. The second one is Babak Anasori, and third one is Michel Barrasom. Both three belongs to Drexel University. Now, this is the assessment based on publication of article which is based on MXene. Now, this journal published 535 literatures based on MXenes, that is Chemical Engineering Journal, and second position is ACS Applied Materials and Interfaces. And now this is the assessment based on keywords. The maximum in all the literature, the maximum 4834 times the keyword which is used, that is MXene, and 1955 times that is the performance, and 1548 times that is the nanosheets, and 1468 that is graphene. So this is the various keywords used in different literatures of which is based on MXenes. Now, these are the different challenges associated with the MXene. One is scalability, stability, and developing hydrofluoride free and cost effective synthesis routes. Researchers are working on this. So this is a developing area. Now people are working on green synthesis also. Only and second and the last is only a few transition metal nitrides have been made, because mostly MXenes which has developed based on carbides. So nitrides is very few papers which is based on nitrides. So these are some references I have used